Hi, this is Spencer, and I'm going to be talking about the memory transfer optimization of bandwidth and memory interleaving. First off, I'm going to start with bandwidth. So increasing bandwidth, if you look on the left of the screen, this is your k equals 1, which is your no optimization. This is a regular memory with your addresses. With increasing bandwidth, with k equals 2, you still have one memory chip, but you're splitting that no optimized memory into two separate pieces. And then both of these pieces are getting addressed at the same time. And as you see, with no optimization, the addresses go 0, 1, 2, and so forth. Whereas in k equals 2 with the bandwidth optimization, the addresses are staggered between the two pieces. So the piece on the left is 0, piece on the right is 1, and then so forth, 2, 3, 4, 5, and so forth. This means that both sets of memory are addressed at the same time. This is shown with if you put it into an Excel sheet, this shows that after the address is read, both of your data transfers happen at the same time, And if we go back, k equals 2, 2 is equal to the number of pieces that you split your memory into. If k equals 4, you have 4 pieces of memory that it is split into. And that would also mean that in your chart, you would have 4 data transfers immediately following your address. If we look at the equation of T block, which is the time to transfer one block of memory, is equal to B, which is the block size, divided by K, which is our bandwidth optimization, and then multiplied by T address, which is the time for address lookup, plus T data. This is the equation. And if we have a simple example down here where we have a block size 64 bits, we have a bandwidth optimization of 4. We get 64 divided by 4 multiplied by 10, which is our time for address, plus 2, which is our time for data. And we get that T block would be equal to 192 CPU cycles. The second form of optimization is memory interleaving. Again, on the left, this is our no optimized 1 kilobyte of memory, just as a representation. With M equal to 2, we're still going to do the same thing as we did in the bandwidth optimization, where we split that memory into two pieces. And again, M equals 2. Whatever M is equal to is the number of pieces that you split that memory into. And again, we are addressing both chips of memory at the same time. But in this case, we have our data moving downward into a mux, where that only allows one data to be transferred at a time. This is shown in, again, a simple chart where you have your address and then you have your data immediately following, but instead of bandwidth being all at once, it is staggered because of that mux at the bottom, we are only getting one data transfer at a time. And again, if this was M is equal to 2, M equal to 4, you would have 4 data transfers. Whatever M is equal to is the number of transfers you'll have afterwards. This is shown by the memory interleaving equation, which same as bandwidth, you have your T block time to transfer is equal to block size divided by your memory interleaving optimization multiplied by your time for address lookup plus memory plus your memory interleaving optimization times your time for a data transfer. And if we use the same values as we did in the bandwidth optimization, you can see that if you use 64-bit block size with a four memory optimization, interleaving optimization, and a 10 cycle address lookup and a 2-cycle data lookup, 2-cycle data transfer, you see that after your equation, you get it to equal 288 cycles. This means that bandwidth is obviously a much more efficient form of memory transfer optimization. And that is, in a nutshell, the memory transfer optimizations of increasing your bandwidth or memory interleaving. Thank you. And thank you for a great semester, Professor. Have a great summer.